Let's take a look at another example of generating an EMF. And I forgot to say, this example where it's moving in and out of the field is one example of what's called motional EMF, which is, I moved my paper down, it's called motional EMF because the loop in question is moving. Let's take a look at another example, and this one is in the book, and it's kind of interesting. So you've got these wires that extend upward, and the wires are just chilling there, and they're attached to a light bulb. And there's this rod on the wire, and this rod is free to slide. The wires are, it's stationary, but the rod is free to slide, and this rod kind of closes this circuit. Now, in this whole region of space, there's a B field, and we'll say it's pointing out of the page. All right. And so what's going to happen here? Well, as we let this rod fall, gravity is going to pull it down. But as it goes down, we've got a flux that's decreasing in the out-of-page direction. Okay, because the flux is decreasing in the out-of-page direction, that means that there will be a current induced in the loop that opposes that change. So if the flux is decreasing out of the page, the current will generate a B field coming out of the page. Okay, so that means that there is there's a B. It will generate a B field coming out of the page, which means that the current will flow around this way in the counterclockwise direction. So we've got current flowing this way, which means that the current inside this rod is to the left, which means the force on the rod, or the magnetic force on the rod, is, we point to the left, and then our middle finger goes up, or we curl our fingers upward, depending on, however you do your right hand rule, and that means up, not up, out of the page, and our thumb points toward the top of the page, so the magnetic force on the rod points upward. And this magnetic force, the current that's generated is proportional to the change in flux. So gravity will accelerate this rod, and it'll get faster and faster. But once it gets to a certain speed, this magnetic force is increasing with the velocity. And so once it gets to a certain speed, this rod can fall at a constant. The rod will eventually start falling with a constant velocity as that magnetic force becomes equal to the gravitational force acting on the rod. And we'll do more to quantify that next time. Another neat example of where this is used is in an induction stove. An induction stove. My family actually has an induction stove back home. But in an induction stove, the surface of the stove is some kind of insulating material, usually like a glass or a ceramic sort of material. But there's a coil underneath where, traditionally you would call them a burner because the coil just heats up and you attach the pan there and then there's just heat. But the induction stove, the stove doesn't actually heat up. There's just a current in this coil that's underneath the stove surface, and that current, it generates an alternating current. So the current will flow in one direction and then it'll bounce back, and as it changes direction, then the flux through the pan, the magnetic flux through the pan that's sitting on the stovetop is changing. And so there's an EMF, and so there's a current that's being generated in this conducting pan. And as there's a current in this conducting pan, well, this pan is made out of, a material that has some kind of resistance. And so there's heat generated, just straight up, power equals I squared R. There's heat generated in the pan because of the changing current in this coil that's below the stovetop. I thought that was pretty cool. Another example of a thing that uses magnetic braking is a speedometer, and this one might be a little more difficult to wrap your head around. So there's a magnet, and this magnet, it's a magnetic thing that rotates, and it rotates kind of along with the tire, right? And so it rotates faster as the car goes faster, and it rotates more slowly as the car goes more slowly. Okay, and so there's this magnet that's rotating, and then this magnet is inside a metal cup. It's inside the metal cup, and so as this magnet is rotating, it's inside a kind of a metal shell around it, and the changing magnetic field creates a changing flux through this metal cup, and that induces an opposing current, which then exerts this magnetic braking effect. That current opposes the change in flux, and so it tends to, oppose the motion of this little, magnetic thingo. And there's a spring attached to the cup, and so this spring, so the cup will rotate because there's this magnetic force being generated on it, as it creates a current that counteracts the rotation of this magnet. Then there's a magnetic force on it, and the magnetic force on it causes it to start to spin. But then this spring is situated to stop the spinning, and then there's this needle, that's on the speedometer that points to whatever the speed is. And so when the spring gets compressed down, and when the spring force equals the magnetic force, then the thing will stop, spinning. The cup will not spin, and that makes the needle stop at a certain point. And with the gauged appropriately, that will tell you the speed of the vehicle, because the speed of this rotating magnet is proportional to the speed of the vehicle. And I thought that was another interesting sort of application.